All right, today we're going to dive into a set of rules so powerful, so fundamental, they basically run the entire universe. We're talking about Sir Isaac Newton's three laws of motion. And trust me, once you get these, you'll never look at the world the same way again.
So let's start with a little puzzle. Think about this for a second. You've got a soccer ball flying through the air, and then you've got a planet, like Earth, orbiting the sun. What on earth could those two things possibly have in common?
Well, the wild thing is, they're both following the exact same rulebook. Yep, a simple set of three laws, written way back in 1687 by Sir Isaac Newton. These rules completely changed everything we thought we knew about how the universe works.
Now, to really wrap our heads around these cosmic rules, we're not going to start out in deep space. Nope, we're going to start with something a lot closer to home.
Just the simple act of kicking a soccer ball. Believe it or not, every single thing you need to know to unlock all three of Newton's laws is right there in that one motion.
So, just picture it. The ball is sitting there on the grass, perfectly still. Why doesn't it just, start rolling on its own? The answer to that is Newton's first law.
You'll often hear this called the law of inertia. And really, at its heart, it just means that things are kinda lazy. They want to keep doing whatever it is they're already doing.
Let's dig into that idea of inertia for a sec. It's not some invisible force. It's just a basic property of, well, everything. You can think of it as pure stubbornness. The more stuff something has, the more mass, the more stubborn it is about changing its motion. That's why it's a whole lot harder to push a car than it is to push a shopping cart.
So let's go back to our soccer ball. Its inertia was keeping it perfectly still. Then your foot comes along. That's the unbalanced force and completely changes its situation. Now it's flying. And once it's in the air, its inertia wants it to keep going in a straight line forever. Of course, we know it won't, because here on Earth we have other forces like air resistance and friction that'll eventually slow it down and bring it to a stop.
Okay, so the first law tells us why the ball moves. But what about how it moves? I mean, a little tap is way different from a huge kick, right? The results are totally different. To understand that, we need law number 2.
And this brings us to probably one of the most famous and powerful equations in all of science. Force equals mass times acceleration. F equals m. It's so simple, but it perfectly explains the relationship between how hard you kick, how heavy the ball is, and how quickly it speeds up. Now hang on, before we go any further, we have to clear something up that trips a lot of people up. The difference between mass and weight. Mass is how much stuff is in an object. It never changes. Your mass is the same on Earth, on Mars, or floating in space. Weight, on the other hand, is a force. It's the pull of gravity on your mass. So while your mass is constant, your weight changes depending on how strong gravity is. In F equals ma, the m is for mass. That's the one we care about. Let's just try it out. Let's say we have an object with a mass of 10 kilograms, and we want it to accelerate at 5 meters per second squared. We just pop those numbers into our formula. 10 kilograms times 5 meters per second squared gives us 50 newtons of force. That's it. It shows you that if you want more acceleration, you either gotta push harder or you need to push something with less mass. It's that simple and that powerful.
So we've covered why the ball moves and even how to calculate its motion. But there's one last piece of the puzzle. When you kick that ball, you feel it, right? Your foot feels a little sting. That's Newton's third law in action.
You've probably heard this one a million times. For every single action, there is an equal and opposite reaction. No exceptions.
But wait a minute, this leads to a super common question. If your foot pushes on the ball with the exact same force that the ball pushes back on your foot, then why does the ball go flying across the field while you barely move at all? Shouldn't the forces just cancel each other out?
And here's the brilliant solution. The forces don't cancel out because they are acting on two different objects. The action force from your foot acts on the ball. The ball has very little mass, so that force sends it flying with a huge acceleration. But the reaction force from the ball acts on you, and your entire body has way more mass, so that same amount of force results in a teeny tiny acceleration that you barely even notice. It's all about where the force is being applied. And the truly mind-bending part? Every single force in the universe comes in a pair like this. Nothing ever pushes or pulls by itself.
Okay, so we've seen how all three laws work together perfectly in something as simple as a soccer kick. Now, let's zoom out. Way out. Let's see how these same rules apply to everything else. A rocket launching into space, that's pure third law. The rocket pushes gas down, action, and the gas pushes the rocket up, reaction.
Ever wonder why a giant semi-truck takes so much longer to stop than a little car? That's the second law. More mass means you need a lot more force to slow it down. And what about the moon? The first law, inertia, wants to fling it in a straight line out into space. But the force of Earth's gravity is constantly pulling it back, creating that perfect, stable orbit. It's a beautiful cosmic dance.
Honestly, it is impossible to overstate how important these laws are. They're not just for physics class. They are literally the foundation of our modern world.
Now, Newton didn't just pull these ideas out of thin air. He was building on the work of brilliant minds before him, like Galileo. But in 1687, he put it all together in his masterpiece, Principia. And now, more than 300 years later, we still use these exact same principles to design cars, build bridges, and launch rockets to Mars and beyond.
And that's really the beauty of it all, isn't it? Just 3 simple, elegant rules that connect the smallest little nudge to the grand, sweeping movements of the entire cosmos.
So, I'll leave you with this to chew on. From throwing a baseball, to driving your car, to just getting up out of a chair, you are constantly, and I mean constantly, playing by these rules. Now that you know them, what are you going to see differently?